Good morning. Hope everybody's doing all right today. So today the plan is we're going to finish up that example 4 from section 2.6. Like I said, that won't take too much longer. It's just a couple more steps to simplify it. Then we'll get into section 2.8. We might actually finish up 2.8 today. We'll kind of see how it goes. If not, then we'll finish it tomorrow and review tomorrow. Either way, we'll get to the review tomorrow. And then by the end of the week, we'll be into chapter 3. Don't forget the test will be posted at midnight tomorrow night, regardless of where we get to today and tomorrow, because we'll definitely finish up the chapter by tomorrow. So test posted tomorrow night at midnight, and then due by Friday at midnight. So just make sure you're carving out some time, Thursday, Friday, to sit down and take your test. The other things that are coming up this week, the 2.4 to 2.6 homework is due by midnight tonight. So just make sure if you haven't finished that one up, make sure you get that done by tonight. And then the 2.8 homework, which is what we're going to cover today and possibly tomorrow if we don't finish today, that'll be due on Thursday at midnight. Okay, so either way, you should be able to get both of those homeworks done this week. Test due on Friday. And like I said, we'll get into chapter 3 before the end of this week. And that way we can continue. And hopefully that next homework on chapter 3, I'll probably push it back a day or two, but it shouldn't get pushed back too far, okay, because we should get into that section. All right. Any questions, comments, concerns about anything before we get started today? All right, as always, if you have questions on the homework, use that Ask My Teacher button, send me those questions. If you want to actually see me work through a problem, feel free to use my student hours before class to come ask those types of questions, okay? All right, let's take a look here to finish this one up now. So we've gotten to the point where we basically have the second derivative. The only issue now is we've got this fraction within a fraction. So we got to think about how we can simplify this, get rid of that. So what do you think we might be able to do at this point so we can get rid of that compound fraction? Okay, so think about it this way. If I want to get rid of a y cubed in the denominator of that fraction, what would I need to do to get rid of that y cubed down there? Multiply, right? Okay, so we're going to multiply by y cubed, and then whatever I do in my numerator up here, I also have to come down here in the denominator and do the same thing. Okay, so anytime you're trying to get rid of a compound fraction like that, look for your denominator, multiply top and bottom by whatever that denominator is. Well, if I do that now, we just have to make sure we distribute that y cubed to everything that we have in this numerator now. Okay, so that's the key. So when I do that, what's that going to give us for that first term now? So I'm distributing this y cubed all the way down here. Perfect, right? So we're going to get a negative 3x squared, and then we have a y cubed times a y cubed. Adding those exponents together should give us y to the 6th power. Now, when I multiply it by the second term, all I'm doing is canceling out the y cubed in the denominator. So now I'm still left with 3x cubed y squared, and then we have this negative x cubed in there now, okay, because the y cubes cancel out. Now, what are we going to have in our denominator? Good, y to the 9th, because again, I'm just adding those exponents. 6 plus 3 gives us 9. Now we can actually simplify that second term in the numerator because I've got some x's that I can combine. So if we do that, we have negative 3x squared y to the 6th. When I multiply this, I'm going to get a negative, so that becomes a minus. We have our 3. X cubed times x cubed is going to give us to the 6th. Okay, and then y squared. All right, so Hyro, when we distribute this y cubed to this term right here, notice all of this stuff is being multiplied together. So all that happens is that the y cubed in the denominator and the y cubed that we're multiplying by, those cancel out, and that y squared stays. Does that make sense? Okay. Yeah, so that's the whole point of multiplying by that y cubed, is to get rid of the one that's in the denominator there. So that other y squared, we don't even have to touch it. We're just canceling out the y cubed in the denominator. All right, and then we still have all of this over y to the 9th power. Now, the only other thing you could do here, and again, it's not a necessary step, but there's some y's in common with all of these terms here. So if you wanted to take out a y squared from the numerator and cancel out 2 of the y's in the denominator, you could do that. So another way to write this would be negative 3x squared. This will become y to the 4th power now because we're taking out 2 of the y's, minus 3x to the 6th. That y squared cancels out. And then down here now we just have y to the 7th power since 2 of those go away. Again, if you don't go all the way that far, if you stop right here, I'm going to give you full credit for that problem. But again, don't leave the compound fraction. Make sure you get rid of that at least. But if you wanted to simplify this and cancel out some of the y's, you could. Any questions on that one now? And just to kind of go back to yesterday to remind you, anytime you're taking a second derivative of something, if you get a first derivative within that second derivative, like we did right here, just make sure you go back and actually substitute the first derivative in so that we have everything in terms of x and y. Okay, because all of our derivatives, first derivatives, second derivatives, third derivatives, no matter what, always need to be in terms of x's and y's. There shouldn't be any derivatives within a derivative. All right, so that's all we've got for that section. Like I said, now we're going to move on to 2.8, which is our last section that we're going to cover in this unit. All right, and so 2.8 is called related rates. And so what we're going to look at in this section is, over time, how are things related in the way that they're changing, right? So their rates of change, if they're related to each other, how are they related? And then how can we use that information to actually find, well, what is the volume of this object going to be if it's increasing at a certain rate compared to its radius, or things like that, okay? All right, so example 1 here, we've got air being pumped into a spherical balloon so that the volume increases at a rate of 100 centimeters cubed per second. We want to figure out how fast the radius of that balloon is increasing when the diameter is 50 centimeters. All right, so what we know in this case is that we have a volume that's increasing at a steady rate, right? 100 centimeters cubed per second. The issue, though, is that the radius itself is not going to be increasing necessarily at a consistent rate like the volume is, right? Because if the volume's increasing at a steady rate, depending on how large that balloon gets, that's going to affect how fast the radius is actually changing. So we've got to set up an equation now and think about how these rates are related to each other so that we can figure out how fast that radius is actually changing when the diameter is 50 centimeters. okay? Now, first thing you always want to do on a problem like this is figure out the formula that you're going to be working with. So based off of what we're looking at, the object and all the information that's given, what formula do you think we might want to use here? Good, right? So we're dealing with volume. We know it's a spherical balloon, so we're going to deal with the volume of a sphere. Well, if you don't know the volume of a sphere formula, that's fine, right? I'm not going to expect you to memorize all the geometric formulas that are out there. Some of them I would expect you to know, right? Pythagorean theorem is one that we'll use a lot, so I would expect you to know that. But a lot of these volume formulas and stuff, I would give you on the actual test. So don't stress if you don't know them off the top of your head, okay? Now, volume of a sphere, though, is going to give us 4/3 pi r cubed. So that's our formula we're going to use here. Now, let's think about what we know. Okay, so what's one piece of information that's given to us? Okay, now, are we given an actual volume? Are we given some information about the volume that's not the actual volume? It's about the volume, right? Now, let's think about what this actually tells us then. So 100 centimeters cubed per second is not a volume. It's actually a rate of change of the volume because it's telling us it's changing at a rate, increasing at a rate of 100 centimeters cubed per second. So now we just have to think about, well, it's a rate of change of the volume with respect to what? Not the radius. So think about the units that you've got here, right? 100 centimeters cubed would be a volume with respect to what unit? Seconds, right? And seconds is a measure of what? Time. So this gives us dv dt. So it's a rate of change of your volume with respect to time. So centimeters cubed per second is dv dt. Now, what else are we given here? We're given a diameter, right? Now, in this case, for our formula, we're actually going to need the what? We're going to need a radius, right? So how can we get the radius from the diameter? Yeah, just cut it in half, right? So if we cut that in half, what's our radius going to be? So the diameter is 50. And so if we divide that by 2, what's our radius? 25, right? Now we know 25 centimeters is our radius. We know 100 centimeters cubed per second is our derivative of our volume with respect to time, dv dt. So what we're going to have to do now is actually come down here to our volume formula, and we're going to take the derivative. And we're going to use implicit differentiation because I've got two different variables here. But we're taking the derivative with respect to time since I know what dv dt is equal to. Well, if I take the derivative with respect to time, what's the derivative of v going to look like? So if I just take the derivative of the left-hand side of this equation, derivative of v with respect to time is going to give us what? Okay, you could call it v prime, right? But what I'm going to do, just to make it clear that we're taking the derivative with respect to time instead, I'm going to actually call it dv dt right now. And the only reason I'm doing that is because in a lot of these, we're going to have so many different variables that we have to be clear that we're taking the derivative with respect to time. So instead of v prime, I'm going to call it dv dt. Now, on the other side, right, if we take that derivative, that is going to give us 4 pi r squared. But because we're taking the derivative with respect to time, what else do we have to include here? Not v prime, because now we're actually taking the derivative of what variable? So on the right-hand side, we've taken the derivative of what variable? Not t. That's what we're taking the derivative with respect to, but we've actually taken the derivative of what variable? So what's our variable on the right-hand side? The r, right? So we're taking the derivative of an r with respect to time, which means I need dr dt now. So on the left-hand side, we're just taking the derivative of volume, so it becomes dv dt. On the other side, we just use our power rule. 3 times 4/3 gives us 4. Pi is a constant, so we keep it. Drop the exponent by 1, that gives us the r squared. But again, because it's implicit differentiation, we're taking the derivative with respect to time. I also need a dr dt on that side now. Any questions about finding that? So drdt it's a variable, right? Because we can actually solve for it, we can substitute in place of it, but it represents a rate, right? So just like if you're finding y prime, that's a rate of change of a function. Now we're saying that this drdt represents the rate of change of your radius with respect to time, but it is a variable, right? It's something that we can solve for. Any other questions there? And the other reason it's variable is because it varies. Okay, so depending on what values I substitute in here for my dv dt and my radius, that's going to affect the rate of change of that radius now. Okay. Now, let's think about what we're trying to solve for and what other information we know. Okay, so do we know dv dt? Yeah, right. So that was given. That's 100 centimeters cubed per second. So I can substitute 100 in place of dv dt. Now 4 pi is constant, so I've got 4 pi. Do I know my radius, my r value? Yeah, right. That was all given. The diameter was 50, the radius is 25. So we can put 25 squared. And in this case, we want to know how fast is the radius increasing, which means we're looking for the rate of change of the radius with respect to time. We need to solve for dr dt. So that's the thing we're actually looking for this time. Now, if I want to solve for dr dt, what are we going to have to do next? Okay, good. Get it by itself. Now to do that, I'm going to go ahead and simplify what we've got on the right-hand side here. So if I multiply that stuff out, just keep pi in there. But if we multiply 4 times 25 squared, what's that going to give us? Okay, so 25 squared is 625, and then we can multiply that by 4, and that should give us 2500 pi dr dt. And then how are we going to get dr dt by itself then? Just divide, right? So we get 100 over 2500 pi equals dr dt. And now if we simplify that fraction, right, what's that going to simplify to? Good, right? So the 100 over the 2500 just becomes 1 over 25. So now we have dr dt equals 1 over 25 pi. And now the only other thing we have to remember is units. Okay, so let's think about what our units are going to be on this. So we've found dr dt, which is the rate of change of the radius with respect to time. What do you think that unit is going to be here? Perfect, right? So the radius is measured in centimeters, our time is measured in seconds. So that's 1 over 25 pi centimeters per second, our rate of change of the radius. And that's it. So, in general, when you see a problem like this, first step, if you can draw a picture, right? Because a lot of times that's going to be helpful, and we'll see that on some of these other examples. Then figure out what formula you're actually working with. Since we're dealing with a sphere and we're dealing with volume, that tells me immediately I'm looking at the volume of a sphere. I'm going to find that formula. Then we're going to take the derivative using implicit differentiation here with respect to time, though, always, right? Because in this case, our rate of change was with respect to time. So we find dv dt. Don't forget when we take the derivative of the r, then we also need the dr dt, since that's what we're taking the derivative with respect to. Substitute everything you know, and then solve for the thing that you're missing. Now, in some cases, you're going to start substituting in and realize you're still missing stuff. You might have to go back and do some more calculations to figure out the missing information. Okay, and we'll look at an example like that in just a little bit too. Any questions on this one now? All right. Example 2. So we have a ladder 10 feet long resting against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, we want to know how fast the top of the ladder is sliding down the wall when the bottom of the ladder is 6 feet from the wall. All right. What do you think we should do first here? Draw the picture. Good. Okay, so anytime you can draw the picture to help you visualize what's going on, that's a good idea. So what can we draw in our picture? Okay, it is going to look like a right triangle. Okay, we have a vertical wall, we have the floor, and then we have this ladder that's leaning against the wall. So I'm going to draw my vertical wall over here. I'm going to draw the floor down here, and then we have this ladder leaning like this. And so it does form a right triangle when we do that. All right, now let's think about what information is given here. So what's one thing we know? Okay, so the ladder is our hypotenuse of the right triangle, and we know it's 10 feet long. So I'm just going to say our C value here is 10 feet. Okay, what else? Okay, the bottom side is going to be 6 feet, right? So I'll call this side B. Because it tells us here the bottom of the ladder is 6 feet from the wall. So we know the length of that bottom side there is going to be 6 feet. Good. What else do we know? We know one of our rates, right? So if we read this, it says the bottom of the ladder slides away from the wall at a rate of 1 foot per second. Well, what is that going to represent then in terms of the picture that I've drawn here? How would we label that? Okay, so first off, it's the rate of change of which variable here, based off of what I've drawn in my picture. B, right? Because that's telling us now how fast it's sliding away from the wall. That's how fast B is changing now. So we know it's going to be dB something. And now we're taking that derivative with respect to what? If it's 1 foot per second. Okay, seconds is a measure of what though? Time, right? So I know now that this is going to represent dB dt, and that's going to be 1 foot per second. So the 1 foot per second tells us how fast the length of the base, right? How fast the ladder sliding away from the wall, how fast is that changing? That's going to represent dB dt now. Now, what are we looking for? What are we trying to find? Okay, we're looking for a rate specifically of how fast the top of the ladder is sliding down the wall, right? Because it's asking us how fast is that ladder sliding down the wall now? Which means, how would we label that variable that we're looking for? Exactly, right? So we know this side over here is going to be A. We don't know how long A is, but if we're looking for the rate of change that it's sliding down the wall, we're trying to figure out how fast is A changing. So this is actually what we're trying to solve for now. Right. Any questions on the picture or how I've labeled anything at this point? Yeah, Hyro.
All right. So let me understand. So A is just like the length, but the dA over dt is the rate that we're trying to find.
Exactly, right? So that's how fast A is changing with respect to time now.
That makes sense.
Okay. Any other questions there? All right. Now, what formula do you think we could use to solve this? Exactly, right? So we're dealing with a right triangle. We're dealing with an A, B, and C value. We're going to use Pythagorean theorem. So remember Pythagorean theorem, A squared plus B squared equals C squared. Now, before we start substituting anything in, because at this point, we know that B is changing, right? So we can't substitute anything into Pythagorean theorem, even though it looks like 6 could be substituted here. We're not allowed to do that because 6 is varying, right? It's not a constant 6. So we're going to have to take the derivative. So we're going to go term by term here using implicit differentiation, and we're going to take our derivative with respect to time. So looking at A squared now, what's that derivative going to give us? Okay, good. So 2A. But again, because it's implicit and we're taking the derivative with respect to time, what else do we need here? dA dt. Good. Right. Plus, what about our second term if we take the derivative of B squared? Perfect. We have a 2B, and then we're taking the derivative with respect to time, so we need dB dt. And then finally, on the right-hand side, we're taking the derivative of C squared with respect to time, which is going to give us what? You got it. 2C dC dt. So that's the key here. Remember, we're always taking the derivative with respect to time. You always need those dAdts, dBdts, and dCdts. Okay. All right. So the two coming from, so using power rule, right? If we just bring the two out front and drop the exponent by one, the A squared gives us the 2A. Same thing with B squared, that gives us 2B, and then C squared, same thing. Okay. Any other questions on finding that derivative now? All right. Now, Dean, I saw you say, wouldn't it be zero? So what's going to be zero? Which one were you referring to? Okay, good. C is not changing, right? So C in this case is the ladder. The ladder is a fixed length. Therefore, its rate of change is going to be zero. So dC dt is 0 feet per second. So remember, dC dt just represents the rate of change of C. C is a fixed length ladder of 10 feet. Therefore, it's going to have a rate of change of 0. Now, let's think about what we can substitute in here then, right? So if we go through, we have 2 times A. Do we know what A is? No, we don't, right? Okay, so that's going to have to stay A for right now. We know we're looking for dA dt, so I'm going to keep that dA dt. Plus, then we have 2 times, do we know our B value? 6, right? Okay, so that was given to us. And then dB dt, same thing. We were given that. We know that 1, so we can plug that in. Equals, then we have 2 times C. Well, C is the 10, but its rate of change is 0. So that's what we're going to get there. All right, so what's the only thing we're missing now that's keeping us from being able to find dAdt? We need A, right? So do you see a way at this point that we could find our A value? Okay, so and it technically is trig, but it's even more basic than that, right? So what formula could we use now to solve for A based off the information we know? Yeah, so now we can actually go back to our Pythagorean theorem. We can plug in the 6 and the 10 to figure out what that A value is at that moment in time, and then we can substitute it in, right? So I'm just going to use Pythagorean theorem up here. So we're going to have A squared plus 6 squared equals 10 squared. So then if we simplify that, that's going to give us A squared plus 36 equals 100. When we subtract now, we get A squared equals 64. And that means our A value is going to be what? 8. Perfect. So now we know at that moment in time, right, as the ladder's sliding away from the wall, that's what our height is going to be. So now I can substitute that in. So we have 2 times 8 times dA dt plus, go ahead and multiply this out. 2 times 6 times 1 is just going to give us 12. And on the other side, all that multiplied together should just give us a 0 now. Now it's just a matter of simplifying and then solving for dA dt. 2 times 8 is 16. dA dt. I'm going to go ahead and subtract the 12, move it to the other side. So we're going to get a negative 12 over there. And so when we solve for dA dt, what's that going to give us? Good, right? So dA dt is going to be negative 12 over 16. 4 goes into both of those values, so we get negative 3 over 4. Now, again, we need to think about our units. Okay, so what are the units going to be on that rate of change? Feet per second. Perfect. So all of these links will be in feet per second, right? Because the ladder's changing at a rate of feet per second. The length at the bottom is also changing at that same rate. And then the height here is also going to be measured in feet per second. Okay, now, why do we get a negative value this time? It's shrinking, right? Since it's sliding down the wall, the length of that is actually getting shorter. And so that's why we get a negative rate of change for that. So always keep that in mind as you're finding these values. Make sure that your answers make sense, right? If it's a length that's changing in a decreasing fashion, then you know you should get a negative rate of change. In this case, as it's sliding away from that wall, the bottom of that is actually getting longer. And that's why we use a positive 1 foot per second to represent that distance. Okay. Any questions on that one now? Okay, and again, just general procedure for these types of problems. If you can draw the picture, draw the picture, fill in everything you know, figure out what formula you're going to be using, take your derivative with respect to time, plug everything you know in there. If you're still missing anything, go back and figure out how you can find it, and then solve for the variable that you're looking for. Okay. All right, example 3. So this time we've got a water tank. It's in the shape of an inverted circular cone, has a base radius of 2 meters and a height of 4 meters. It says the water is being pumped into the tank at a rate of 2 meters cubed per minute. We want to know the rate at which the water level is rising when the water's 3 meters deep. All right, so what's our first step going to be here? Okay, let's draw the picture, right? So we know we're looking at an inverted circular cone, basically like an ice cream cone is what we're looking at. So I'm going to go ahead and sketch that. I have my circular base up here, inverted circular cone, something like this now. All right, now let's think about what we can actually put in our picture, what information we're given. So what's one thing we could label here? All right, so we know the radius of our base is going to be 2 meters. So that's from center out like this is 2 meters. Okay, what else do we know? We know the height is 4 meters, right? So the total height, like this, 4 meters. Okay, what else do we know? Okay, the water level itself is 3 meters deep, right? So I'm going to draw this in here. So the water itself is not all the way to the top, right? It's going to be right in here. And so that water level is 3 meters. All right, what else do we know? Okay, so we know we're going to be dealing with a cone. We know we're dealing with volume, right? So the formula we're going to use here, volume equals 1/3 pi r squared h, right? Okay, so that's our volume for a circular cone. Now, what's the last piece of information that's given here? Okay, our rate is 2 meters cubed per minute. So that's the rate of change of what? The volume, right? So how are we going to represent that? What variable are we going to use to represent that rate of change of our volume? dV dt, perfect. So we're given dV dt, and that's going to be 2 meters cubed per minute. Okay? All right, so we've got our picture. We've pulled out all the information we know from the problem. We know what formula we're dealing with because it is a cone and we're trying to find volume in this case. What are we going to do next? Okay, before we can plug anything in, what do we have to do first? We have to take the derivative, right? Now, when we take the derivative this time, what rule are we going to have to use to find our derivative? Think about what operation we've got going on. It is a product, right? So since we've got 1/3 pi r squared times h, right, two different variables being multiplied together, we've got two different functions basically being multiplied. We are going to have to use a product rule in that current form. So you could think of f as 1/3 pi r squared, and then your g would just be h. So what would our f prime be equal to in this case? Okay, 2/3 pi r. And then don't forget, because we're taking the derivative with respect to time, we also need the dr dt here. Good. And then our g prime is going to be what? Okay, so 1 dh dt, right? So this is just going to give us dh dt. Again, because we're taking the derivative with respect to time, the derivative of h is dh dt now. Any questions about that? All right, now let's substitute everything in here. So remember, derivative is going to be fg prime plus gf prime. Coming back over here, derivative of v is just going to give us dv dt. That's the left-hand side. Now on the right-hand side, I'm using that product rule, so we're going to start with f. So we're going to have a 1/3 pi r squared. Multiply that by g prime, which is just dh dt, plus, and we're going to have our g function, which is just h. And we're going to multiply that by f prime, which is 2/3 pi r dr dt. Any questions up to that point? Okay, now, if you want to move things around, clean it up a little bit, you could, but at this point, really, we can start substituting things in that we know and then see if we're still missing anything. Do we know dv dt? Yeah, right, that was given. That's 2 meters cubed per minute, so in place of dv dt, I'm going to put 2. And now when we get to the right-hand side, we have our 1/3 pi. Do we know our r value here? Okay, now be careful. We're trying to figure out the rate at which the water level is rising when the water is 3 meters deep. Is the radius going to be 2 when the water is 3 meters deep? It's not, because we're looking for this radius right here when the water level is not all the way to the top. So we know if it was all the way to the top, the height would be 4, the radius would be 2, right? But in this case, our water level is only 3 meters. We need to know that radius. Any ideas on how we could find that radius? It is right triangle math, right? Okay, and really it's more similar triangles than anything else, because if you notice here, we have this triangle and we have this triangle. They share a common angle at the bottom, which means that those two triangles are similar to each other. Well, if they're similar to each other, that means their side lengths have to be proportional. So how could we actually set this up to find that R value then? So we know the overall radius is 2. We know the overall height is 4. We're trying to find the radius when the height is 3, but we know that the side lengths of those two triangles have to be proportional to each other. How do we set it up? We don't actually even have to go tangent, right? We don't have to use any trig here at all. And it doesn't matter what the angle measures of this triangle are. So it's more basic than that. Okay? So if the side lengths are proportional, then we can set up a proportion to solve for the missing side length. Well, in this case, I'm going to say, well, my radius over my height, which is 2 over 4, is always going to be equal to my radius over my height, no matter what. Right? It doesn't matter what height or what radius I'm given. Okay? They're always going to be proportional in this figure. Well, I'm looking for the radius when the height is 3 meters, so I can say, well, 2 over 4 is equal to r over 3 then. How would you solve that? Just cross multiply, right? So that's going to give us 6 equals 4r, which means our r value is going to be what? Oops. Yeah, 3 halves, right? Because 6 divided by 4 should be 3 over 2. So r equals 3 halves. Well, now I have an r value. I can substitute that in. So this is going to be 3 halves squared. Do we know dh dt? Not yet. Now, go back and think about what we're actually looking for. We want to know the rate at which the water level is rising. So we're looking for what? We're looking for dHdt, right? So I'm going to leave that in there because that's the thing we're actually trying to solve for now. So since we're looking for the rate at which the water level is rising, we're looking for the rate of change of the height with respect to time. All right, now we keep going. Do we know the h value? Good. That was given. That's 3 meters. So we can put a 3 there. And we have our 2/3 pi. R is the same R that we just found over here. So we can go ahead and put that in there. That's going to give us 3 halves. Now we need dr dt. Okay, so do we know dr dt this time? Okay, so the radius, right, is 2 for the whole thing. The dV/dt is 2 meters per minute, but we don't know the rate of change of that radius, right? And especially at this moment in time, we definitely don't have that information. So we've got to think about how we can actually get that dr/dt in terms of something else that we can actually substitute in here. Now, the way we're going to do that is we're going to come back to this formula right here, since I know my radius and my height are proportional, and I'm going to try to get dr/dt in terms of dh/dt instead. So all I'm going to do is I'm going to take this formula, 2 over 4 is just 1/2. I'm going to multiply the h to the other side. So this tells us that 1/2 h is equal to r. Again, that's just simplifying 2 over 4, multiplying the h to the other side. Now I'm going to take the derivative of both sides here. If we take the derivative of the left-hand side, what's the derivative of 1/2 h going to give us? One half, but because we're taking the derivative with respect to time still, we also need here a dh/dt. And then the derivative of r is going to give us what? dr/dt. So now we know the derivative of the radius with respect to time is just 1/2 dh/dt. Since that's the variable I'm trying to solve for, I'm going to go ahead and just get this in terms of that. So this is going to be 1/2 dh/dt now. And then that way I have my entire equation. The only variable there now is a dh/dt. That's the thing I'm trying to solve for. So I'm going to pause there. Any questions up to that point? Okay. Now it's just simplifying and getting dh/dt by itself. So let's go through this. We're going to have 2 equals. If we multiply here now, we've got 3/2 squared. We're multiplying that by 1/3. So that's going to give us 9/4 times 1/3. 9 over 4 times 1 over 3 should give us 3/4, if I'm not mistaken, pi dh/dt. And somebody correct me if that's not right math. And then over here, same thing. We're just going to multiply all this out. So we've got 3 times 2/3. Well, that's just 2. 2 times 3/2 is going to give us 3. And then we're multiplying that by 1/2. So that's going to be 3/2 pi dh/dt. All right, now we can actually add these together because they are like terms. So what's 3/4 pi plus 3/2 pi going to give us? Good. So this is 9/4 pi dh/dt. And so then our last step, we just need to divide now to get dh/dt by itself. So we end up with 2 over 9/4. Same thing as multiplying by the reciprocal. So we're really multiplying by 4 over 9 pi. So this just gives us 8 over 9 pi equals dh/dt. And again, the last step is to make sure you've got your units here. So what are the units going to be on DHDT? Okay, almost. Okay, so make sure our height would be measured just in meters, right? So this is actually just going to be meters per minute. So our volume was the rate of change of volume was meters cubed per minute, but the height itself is only going to be in meters per minute. And that's our answer. Any questions there now? Yes, right. So I always want you to consider units when units are appropriate. So in this case, right, you're given meters, you're given minutes, so you know your units for distance and time. So I would expect you to write the units. Now, there will be times where, it's very ambiguous, right? It's just numbers that you're working with. In those cases, obviously, you wouldn't have to worry about units. Any other questions there? All right. So take our break. Yeah, so I know it's a lot, right? So take some time, process it. I'm actually going to come back. We're going to do this same problem, not completely over again, but I'm going to show you where we could have made a little shortcut in here to make it slightly easier. Again, this is perfectly fine, but there is one thing we could have done differently that would make it slightly easier. So I want to go back and show you that. We'll take our break first, take some time to process. And then when we come back, I'll show you that. Okay, and then we'll move on to the rest of the section. Okay, so 11:07, we'll get started back up. All right. So, like I said, I'm going to go back now and I'm going to keep my picture. I'm going to keep the formula we started with and all that. I'm going to erase everything else that we did in terms of the derivative, though, because I'm going to show you we could have actually simplified this function up front before finding the derivative. Okay, so you always want to look for ways, if you can, that might simplify that derivative process. So let's think about what we know in this case. All right, so I'm going to come back down here. We don't need any of this. All right, so I'm just going to start from right here now. What do we know about the relationship between the radius and the height now? Okay, so what's our relationship between our radius and our height? Good, right? We found down here that our radius is equal to 1/2 height. That's always going to be true no matter what the water level is, right? So in this case, before I ever take a derivative, I can actually substitute that information in there because I know it's always true no matter what. So in place of r, I'm going to put 1/2 h. I'm going to get 1/3 pi 1/2 h squared times h. So again, since I know the relationship between my radius and my height, I can just substitute 1/2 h in place of the radius. Now let's simplify this. So over here, we're going to have volume equals 1/2 h squared is going to be 1/4 times h squared. So that's 1/4 times 1/3. That's going to be 1/12 pi. And then this is going to be h squared times h should give us h cubed. Now I'm going to find my derivative. But this time, I don't have multiple variables over there. I don't have to use product rule anymore. I can actually just take the derivative as is. So we're going to have dv dt equals, what's our derivative going to look like on the right-hand side now? Good, right? 3 times 1/12 is going to simplify to 1/4 pi h squared, because we're dropping the exponent by 1. But because we're taking the derivative with respect to time, we also need what here? dh dt. Good. Okay. Now we substitute. We said that dv dt is equal to 2, so I can substitute that in. We have 1/4 pi times h squared. Our height in this case is 3 meters squared, and we're looking for dh dt. Now when we simplify, 3 squared is 9 times 1/4 is 9/4 pi, so we get 2 equals 9/4 pi dh dt. And when we divide, we get exactly the same thing we did before. So this becomes 8/9 pi meters per minute equals dh dt. Same answer, but our derivative was much easier this time, right? So if you can recognize those relationships up front, it could save you some time in your derivative and some possible mistakes, right? Because that product rule is not exactly easy. And you have to look for the other relationship later between the radius and the height to find those values to substitute in. There's a lot more places you could go wrong. Okay, so anytime you can get it in terms of a single variable, it's probably going to make life easier. Now, again, that only works if that relationship is consistent regardless of how things are changing. In this case, the relationship between radius and height is 1/2 height equals radius. That's no matter what the height or the radius are. That's why we can do it. Any questions there now? All right. Example 4. So car A is traveling west at 50 miles per hour. Car B is traveling north at 60 miles per hour. Both are headed for an intersection of two roads. We want to know the rate that the cars are approaching each other when A is 0.3 miles and B is 0.4 miles from that intersection. So what's the first thing we're going to do here? Draw the triangle, right? So in this case, they're heading for the same intersection. Okay, so this is going to be a right triangle, similar to the ladder problem. I'm going to try to draw my directions correctly, though. So the first one's traveling west. So that's going to be an east to west line. He's headed in this direction. And then the other one's going north. That's going to be like this, traveling in this direction. And they're both headed for this intersection up here now. All right, now, what information are we given? Okay, we know their speeds, right? So how could we represent that in terms of the problem here? All right, so we know the legs of A and B, right? So basically what I'm going to do, we know car A is this top side up here, so I'm going to label this A, and then I'm going to come down here and I'm going to label this side over here as B. So how long is A? Let's start with that. Okay, the length of A is 0.3 miles, right? So this is 0.3 miles. And then we know it's traveling at 50 miles per hour, which means that that would be what? How would we label that? That's our rate of change with respect to time, right? So that's dA dt. So dA dt is going to be 50 miles per hour. All right, now, what about B? How long is B? 0.4. And then the rate of change for B is going to, okay, that's going to be 60, right? Because it's traveling 60 miles per hour. So that's the information that's given. We're trying to figure out how fast are they approaching each other, which means we want to know dCdt, right? We want to know how fast is that hypotenuse changing, because that's how fast they're getting closer to each other. Right, so C dCdt. This is the thing we're looking for. So what are we going to use to find that? Pythagorean theorem again, right? So we got a right triangle. So we're going to say a squared plus b squared equals c squared. We're going to take our derivative with respect to time again. We're going to get 2a dA dt plus 2b dB dt equals 2c dc dt. All right. All right, so let's start substituting, and if we're still missing anything that we need, right, then we'll go back and figure out how we can find it. So we've got 2 times a. So what's our a value this time? 0.3. Good. We're going to multiply that by d a dt. So what's d a dt going to be? Be careful in this case. Is that distance getting shorter or longer? Shorter. As you're approaching the intersection, that distance from the intersection should be less, right? So we need to make sure that we're using a negative rate of change for this. So we're going to call this negative 50. Okay. Now we go on to our b. So we have 2 times b. That's given as 0.4. What's our rate of change for b going to be? Negative 60, right? Because again, as he's approaching that intersection, that distance is getting shorter. So we have to make sure we're using a negative rate of change there. Right, now on the other side, we've got 2 times c times dc dt. dc dt is what we're looking for, so we know that. How can we find c now? Pythagorean theorem, right? So we're going to take the a and b values, plug them in, find our c value. So we have 0.3 squared plus 0.4 squared equals c squared. 0.3 squared in this case is going to give us 0.09. 0.4 squared is 0.16. That gives us 0.25. So what's our c value going to be? 0.5. Good. This is 0.5 miles right here. And so we can plug in 0.5 for our c value. Now it's just a matter of simplifying, solving for dc dt. So if we multiply this out, 2 times 0.3 times negative 50, what does that give us? Okay, good, negative 30 plus, and then 2 times 0.4 times negative 60. Negative 48, good. And over here, 2 times 0.5 is just 1, so this is really just dc dt now. Okay, so now if we add those together, what's that going to give us? Negative 78. Good. That's our dc dt. And now we just need to consider our units. So what are the units going to be this time? Miles per hour. Good. So those cars are approaching each other at a rate of negative 78 miles per hour, meaning the distance between them is getting shorter in this case, right? So that's why we need the negative. So negative 78 miles per hour. Any questions on that one now? Okay. Again, overall process, draw your picture if you can, put everything in there that you know, figure out what formula you're using, take your derivative with respect to time, plug everything in. If you're still missing stuff, go back and figure out how you can find it, and then solve for the thing that you're looking for. And that's always the way you're going to do these problems. Obviously, the pictures are all going to be different, the formulas are going to be different, that kind of thing. But the process itself is pretty consistent. right, example 5. So we have a man walking along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path that's closest to the searchlight? All right. What's our first step going to be here? Draw the picture. Good. So let's think about what we know in this case. So what's one thing we could draw here? Okay, so we've got a light 20 feet from the path, right? So, and we know that he's walking in a straight line. So basically, I'm going to draw my path going from left to right up here. So here's my path. And we've got this man. Sorry, my artistic skills are not very good. Okay, there's our man. He's walking down the path. We also know there's a searchlight that's 20 feet off the path, right? So somewhere down here, this is our searchlight. And we know its distance from the path, that the shortest distance, right, which would be perpendicular, is going to be 20 feet. Now, as he's walking, that searchlight is going to stay focused on him, okay, no matter where he is on that path. So let's think about what else we know now. What else can we fill in our picture? All right, so 15 feet. So what is 15 feet going to represent? Where would it go and how would you label it? Okay, it's how far he's walked along the path, right? And so what do you want to, what variable do you want to use to represent that? There's no right or wrong answer here, so whatever variable you want to use. Okay, A1. Okay, so we'll call A 15 feet. Okay, so that's how far he's walked down the path. Okay, we already know 20 feet is the distance of the spotlight from the path. How do you want to label that one? Okay, we'll call that B. This will be B over here, because we are going to have a right triangle, right? If you want to go ahead and connect this, make your right triangle. Like we said, that's going to be perpendicular there. All right, so what else do we know? Good. We know the rate of change that he's walking is going to be 4 feet per second, so that's dA dt. Okay. Now, that's all the information that's given. What are we trying to find? Okay, so be careful here, right? dCdt would represent the rate change of values, right? We're trying to figure out the rate of rotation, right? We want to know how fast is the spotlight actually rotating to stay focused on that man. So we're looking for a derivative of theta with respect to time now, right? Where theta is this angle down here. Right? So like Dean said, we are going to have to use some trig at this point to set this up so that we can actually figure out what d theta dt is, since that's the thing we're looking for. So what trig function are we going to use? And I think you got, oh, you said tangent, good. So this is going to be tangent theta. And what would tangent theta be equal to in this case, based off the information that's given here? Almost, okay? The only reason we can't do that is because the distance that he's walking is not fixed. And so remember, we can only substitute things in that aren't fixed after we've taken our derivative. So what's the only thing here that is fixed, that's not changing? The 20, right? So I'm allowed to put the 20 in the denominator, but in the numerator, I have to use a variable, so I'm going to call it a. So don't substitute anything in there that's changing until after you've taken your derivative. That 15 is not a fixed value, so we can't plug it in yet. Any questions on that setup, why we use tangent and how we got that equation? All right, now at that point, what I'm going to do, I'm going to go ahead and just move the 20 over, get a by itself here. So this will give us 20 tangent theta is equal to a. What can we do at that point? Take the derivative. Good. So if we take our derivative now, what's the derivative of the left-hand side going to look like? All right, so we're going to get 20 secant squared, good, theta. But because we're taking a derivative with respect to time, what else do we need on the left-hand side here? D theta dt. Good. D theta dt. And then the derivative of a then is just going to give us dA dt. Perfect. All right, now we know we're looking for d theta dt, right? That's what we want to know. We're trying to figure out how fast is that light rotating. So we need to know theta and we need to know dA dt. If we can find those two things, then we've got everything we need here. Well, if I want to know secant squared theta, is there a way that I could find secant squared theta in this case without even needing to know what theta is? How would we do it? So rewrite the earlier equation with theta, so tell me where you're looking. Are you talking about the tangent theta equation? Okay, we could do that, right? We could do that, we could find theta, that's fine. There's actually a better way where we don't even need to know what the theta value is, and we won't have to deal with any decimals at all. So think about what we know about secant. Is there a way that we could find the secant value for theta in this triangle without even needing to know how big the angle is? So we have a right triangle. We need to know secant. How would you find secant in a right triangle? Yeah, it's the reciprocal of cosine, right? So if I know the cosine, I can just take its reciprocal and then we're good to go. Well, how do we find cosine? It's adjacent over hypotenuse, right? So in this case, if we can find our C value, then we can just do adjacent over hypotenuse. We have our cosine, we take its reciprocal, we've got secant, we plug it in, we're good to go. How can I find the hypotenuse here? Pythagorean theorem, right? I know A, I know B, let's find C. So we're going to have 15 squared plus 20 squared equals C squared. And so then we can just go through, simplify all of this. So we've got 225 plus 400 is C squared. It's going to be 625, which means our C value is what? 25. Good. You could have also recognized that as a 3, 4, 5 right triangle, right? 3 times 5 is 15, 3 times, 4 times 5 is 20, and then 5 times 5 is 25. All right, now that we know the length of the hypotenuse, now we can find our cosine. So cosine theta would be equal to what? Twenty over 25, right? Because 20 is our adjacent side to the theta. 25 is the hypotenuse. If we simplify that, that gives us 4 over 5, which means secant is going to be what then? 5 over 4. Perfect. So now we know secant. We just need to square it because it's secant squared. So this becomes 5 over 4 squared, multiplying that by d theta dt. And then our dA dt value is what? That was just 4, right? All right, now if we simplify, what's 20 times 5/4 squared? Good, 125 over 4, d theta dt. And now we can just divide to get d theta dt by itself. And if we do that, what do we get? All right, so be careful, right? It looks like the 4s might cancel out in this case, but we're doing 4 divided by 125 over 4. So we're really multiplying by that reciprocal. So 4 times 4 over 125 is actually going to be 16 over 125. All right. Now, last step, we need units. Okay, so what are the units going to be on d theta dt? Okay, so our distances here were measured in feet, but we're finding how fast this thing is rotating. So what did we actually find? So it's not going to be in degrees because we're actually going to, you're close, right? But what unit should we use instead of degrees? We could convert it to degrees, but as is, d theta dt is actually measured in what? Radians, okay? So this is actually going to be radians per unit of time, which was seconds. So whenever you're calculating these, just know it's always going to be a radian measure, right, in terms of your angle, unless you do some kind of conversion to get it in degrees, but otherwise it should be radians. So again, that is the rate of change of rotation with respect to time at that particular moment in time when the person has walked 15 feet. Because that rotation is going to change depending on where they are along the path. Okay, so that's only the rate of change of the rotation at that moment in time. Any questions on that one now? All right, so that's the end of that section. That's all we're covering. I'm not going to start the review with only 10 minutes left, so we'll save that for tomorrow. Like I said, we'll go through the review for the first half of class, and then probably the second half we'll get started on chapter 3. Don't forget, though, by midnight tonight, the 2.4 to 2.6 homework is due. The 2.8 stuff that we just covered, that homework's due on Thursday by midnight. Those problems, as you can see, sometimes some of them take a little time. You're going to have to think through them. So even though that one looks a little shorter in terms of number of problems, just make sure you leave yourself plenty of time to actually work through them. Let me know if you've got any questions. Again, student hours are a great time to ask me those questions if you can drop them in class. Test will be posted midnight tomorrow night, due Friday at midnight. Homework 6, is that the chapter 3 stuff, Rachel? That one's most likely going to be due like Monday or Tuesday of next week is what I'm thinking right now. So you'll definitely at least have the weekend. So for right now, focus on the chapter 2 stuff for sure. I'm sure you have time to do the test. But yeah, the chapter 3 stuff will definitely be after the weekend. Okay? All right. I'll hang out for a few more minutes since we technically have 10 more minutes of class. So if you have any questions, feel free to hang out and ask me those questions. Otherwise, have a great afternoon, and I will see you all tomorrow.